Okay, I suppose I'll just get started. Thank you very much for the invitation, and thank you all for attending. So yeah, this talk I've never given this version of this talk, so let's see how well time it. What I work on really is understanding and modeling speech production and speech perception in the human brain. And right now, as I'm speaking, something remarkable is happening. I am having all these thoughts in my head that I want to convey, and I'm using my vocal apparatus to transmit all those thoughts through the medium of air. And then you are doing the inverse process of understanding what it is that I'm saying. So it's really hypothesized for a long time which where each of these processes and how they are mediated by human production and perception system. And it's a very uniquely remarkable skill, whereas many organisms have very good vision, better than human, or motor skills. Speech production and speech communication is very, very human. And that's what makes it like very interesting and kind of an identity of us as humans. So in this talk, I'll largely focus on this part of the brain and the speech production apparatus, and also with noting that there is more in terms of the perception and production interfaces. And this is not a new endeavor. People have always wondered about what it is that mediates our ability to speak fluently and communicate at high throughput with each other. And this is uh, a slide from Harvey Cushing, an epileptologist, a neurologist who was stimulating various parts of the brain, and he was noting where different parts of the vocal tract exist. So you can see the face. I do not know if the drawing is faint, but there is lips and the jaw and the tongue. And this is 1906. Think about how um, far ago that was, and it was still very interesting that we could do that. And of course, this was extended to other parts of the body. In fact, there is this thing called the motor homunculus, which is like a one-to-one mapping between the cortical surface and different parts of the human body, right? So this is like a very one-to-one evolved connection that has emerged through evolution. Now, that was through electrical stimulation, but what we do now is really through just sensing. So we don't have to stimulate part of the brain to see evoked responses, but we can just measure what's happening in the brain. And there is various things that we could measure. Like we could measure all the way from single neuron activations to the voltages that come up out or the blood flow. So there is all these technologies that we now have, all the way from single neuron to that's at the very low level, all the way through very high level EEG and MEG and fMRI, which scan like the entirety of the brain. But there is always a trade-off between how much space we can sample and what the time resolution we get. So it's a sweet spot that we need. And in my work, we really work with ECOG, electrocorticography, which is this invasive modality of implanting people with electrode sensors that are sitting right on the surface of the cortex while we measure the potentials, the voltage really, as people are doing their yeah, regular things. And this has been used for studying many human behaviors and human perception even. So just to situate what it is that we are working with. So what you're seeing here is the single a single electrode location in the brain as someone is listening to this sound "s." So on top is the average response. So you can see that there is a marked high energy in a particular band of interest, 70 to 200 hertz. And you can also see single trial rasters that are very high fidelity. The signal to noise ratio is excellent. So this is a very unique opportunity because in non-invasive modalities like EEG, you don't get that level of SNR. So it's not scalable in terms of like everyone getting an implant, but certainly it's an opportunity to study the basics of how it is that humans do what we do, and then it will inform the design and modeling of non-invasive work even later. Um, so that's the neural stuff, right? There is also the behavior of speech production, right? The speech production is really the product of lots and lots of muscles and bones structures. So you can see like a lot of apparatus there. Very very complex motor speaking. Maybe the most complex motor action that humans perform is speaking, right? So you can see that there is many articulation, and people have always postulated and studied how it is that we actually produce speech. In fact, it is a very intuitive representation, and I take the example of Korean here, where even the writing system takes advantage of the shape of the placement of where your tongue is in situating what the writing system should be. And likewise, you see on the bottom here is Sanskrit, and most of the Indo-European, the Dravidian and the Indian languages also have this very place of articulation and manner of articulation based arrangement of the sounds of the language. So that is, it's been postulated how it is that we do it mechanistically, but we also need to probe it and measure it, right? So there are certain techniques that we have um, for exactly precisely assaying. Whereas cameras are enough to study like gait or hand motion. You really need, because this is a lot of occlusion here, you need to sense within the closed part of your mouth. So there are techniques like magnetic articulography, where sensors are placed on different parts of the vocal tract, and the subject speaks within a magnetic field, so we can measure the movement of different parts. So what you see here are these traces of lips, tongue, and the jaw. And there is also other modalities like real-time MRI that are getting developed these days. So we have high-resolution sensing of what's happening in the vocal tract even, right? So we spoke about how we're measuring the brain. We spoke about how we're measuring the behavior. So that is all okay. But what happened very recently is the advent of deep learning based techniques for many domains, including spoken language. And kind of for um, uh, the long story short, there is what's driving these big models in AI. These foundation models are really a lot of data, and a very key ingredient of what's called mask prediction, or how well can context predict you know um, a masked token of the language. So what you see here is an architecture. It doesn't really matter, but what we're doing is really masking different parts of your input. So if you take a sentence, you just mask a couple of words in between, and then predict what these would be based on whatever else is happening in the sentence. And that's really is the key ingredient. And this is what's called self-supervised learning, because it doesn't need any labels. It's just massive data and a self-supervised objective. So it has also been done for speech, and it remains the state of the art these days in terms of what we can do. Um, Kind of the framework here for self-supervised learning is you have big data, and you have a self-supervised model with with the loss function that is optimizing that prediction loss or contrastive loss. But that is the foundation model, and then it then is fine-tuned for a targeted downstream task like speech recognition, speaker ID, speaker verification, and so on. So these are the two phases. One is the pre-training, and one is downstream. And that really is the key to enabling this massive performance gains that we are seeing now, that we have never been able to do with like very precise modeling of behavior and or statistical models even, right? So just to summarize, what we can get with the self-supervised models is this is a big number slide, but it really is like phoneme recognition, keyword spotting, intent classification, like all these tasks in speech. And you can see self-supervised methods on the very bottom are like killing it in terms of how well they do. So the question then is, okay, this is all speech AI. Where is brain? Where is the vocal tract here, right? So that really is what we wanted to ask: is like, are these models of large pre-trained models of language, are they grounded in anything? Are they just agnostic to the whole domain of speech production? Does it have a sense of phoneme? Does it have a sense of tongue and the lip and the jaw? You know, we actually initially thought it wouldn't be the case, but to our surprise, it very well was. And here is the setup, right? So what we had done here was we used one of the pre-trained self-supervised learned models. We measured the propagation of the representation all the way from the speech acoustics to the very ending of it, and then see what it is close to in terms of this is what's called a probing experiment. So what we are measuring really is the trajectories of lips and the jaw, but we have a linear regression to go from intermediate layers of these big pre-trained models to these. So this is linear, so we are not attributing any new data in there. We are just affine transformations. And to our very surprise, what we can do, what we see here is across different articulators: lower incisor, upper lip, lower lip, tongue tip, tongue blade, tongue dorsum. So you can see what's in black is actually what's measured within a magnetic field a person was doing as they were speaking a sentence, and what's in the colored traces is actually the decoding from a very simple linear regression model, right? So this to us suggests that these large pre-trained models are figuring out the causal mechanisms underlying speech production. In fact, that really is the key to what enables their very good performance. And another surprise to us was that we don't really need a lot of data to train this simple affine transformation. All we need is like 300 seconds, which is about 5 minutes of speech. Um, my cursor. Yeah. So at about 5 minutes, you see it elbowing. So this is a very representation that is very native to what the SSL models are actually learning. Okay, why are we talking about all this? Because I'm talking about an alignment that exists already between the self-supervised learning models of speech and human articulation. This actually holds up very much so that how good a model is, a self-supervised model is kind of quantified by how well it models the articulatory traces, right? In fact, there is this benchmark called Superb that measures various self-supervised models in the open source domain, and the rank of these models, different models, is actually very well correlated with how well they do on this task of articulatory coding, right? How well it is grounded in articulation is how well it'll do in any downstream task. So that was actually quite pleasing, reassuring that the developments in AI are not to the uh, exclusion of grounded models for spoken language. What's surprising to us that this was also cross-linguistic, and you can see that you can train an English self-supervised model and test on Korean, and in fact that is what these bars are. So whereas each of these columns is one language SSL, and you're testing it on various other language data where you're measuring people in articulation. To us, what this suggests is that there is this common substrate of speech production. So if you want to say mama, whatever be the language, it has to have this jaw lowering and lips closing, right? It is language independent. And that is what we really have shown, that these self-supervised models are actually true universal inversion systems. It's like they invert acoustics into articulation and vice versa. We can also do that. In fact, that is what we have done in a very recent upcoming journal paper in signal processing called the Speech Articulatory Coding, or SPARC for short. Right. So what Spark is a way to both analyze and synthesize speech from articulatory data. Right. So you go from acoustics, as you see here, through articulatory analysis, and you can predict what the lips would be doing, what the tongue would be doing, and you have the synthesis route, which is how do you go back from these movements back into speech. So this is a codec, if you will, but you're going from acoustics into something that's physiologically grounded. And very precisely, that's what we do. We train these big well, we actually not train it, we actually use a pre-trained wave LM transform is what it's called, and we check the layer which is best grounded in articulation, and we use that to basically infer all these points in the vocal tract, the lips and the jaw and the tongue and the larynx. For the larynx, we use the fundamental frequency, or the frequency at which the vocal folds vibrate. Um, and we use also an embedding for speaker identity. All right, okay. It's too much details, but what I want to get to is we now have a way to go from speech acoustics into speech articulation, right? Mind you, the other way to do that is actually collecting data with sensors on people and or putting them in a magnetic MRI machine, and that's just not scalable, right? So, but now we have, with the availability of these large self-supervised models, the ability to infer what they would be doing in the behavior, which is actually quite important if you want to like really model behavior. And so here is an example of what Spark does. So here is a sentence I'm going to play.
This may answer perhaps in a small place where the manager can gauge pretty closely from actual observation.
So it's an English sentence, and here is resynthesized.
This may answer perhaps in a small place where the manager can gauge pretty closely from actual observation.
So it's pretty remarkable. It's lossless perceptually, but we are representing speech not using the FFT, but just using 14-dimensional movement patterns, right? That it's very very low in terms of the temporal resolution, and only 12 in number. Um, and what's more, given the universality across languages, we can also actually transfer across languages. Here, I'll play the Korean example. So here is an original Korean sentence.
인쇄하기 전에 종이가 있는지 확인했어?
And here is the resynthesis.
인쇄하기 전에 종이가 있는지 확인했어?
Okay, what's remarkable is, you don't actually need Korean self-supervised models even. Right? You can just go into this space. And why is this powerful? Because we now have a way to like quantify articulation, right? And I'll tell you why it's important. But what other things it can do is we can completely disentangle identity of a speaker and the content of what they say. I'll just play one example here. So here is an original female speech.
Up to now you may have spoken the truth, but now I know that you have lied.
I want her to sound like this person.
I would have loved to play in an old firm. Up to now you may have spoken the truth, but now I know that you have lied.
So this is zero shot voice conversion. We don't even have like a lot of trained supervised data from these two subjects. We've gone into this very speaker generic representation that is shared across all of us, across languages even, that we can now resolve. Why is this important? This sounds like a very speech tech talk, but no, it's not. It's really for modeling, behavior perfectly and disentangling identity, which is really a result of the geometry of the vocal tract and the physics that entails it. So anyway, and it's also there are other things that are good about this. You can make because this is a very explainable white box model of speech. You can move the tongue back and forth and make it sound like different sounds, right? Which you cannot do with spectrograms typically, right? So here is just an example of like in Korean or Japanese even the L and R are not phonetic changes. They are very allophonic, meaning you have to you cannot really place the tongue properly, but you can. So I'll just play this video where the first is a lock, the word lock, and then in the second, we just pull the tongue back a little bit and then resynthesized it.
Lock, rock, lock, rock.
So lock becomes a rock just by pulling the tongue back. And this is again a power of very well aligned model, a feature representation that's very physiologically grounded. Is like you can make all these manipulations. Now, why is this again important? Because the brain would be coding something that is very aligned with behavior. Well, that's the hypothesis. We'll see if that is correct in a bit. But just to summarize, the Spark work, the speech articulatory coding work, we can align speech AI models with speech articulation, right? They are already aligned. We just have to do a tiny little affine transformation, and you have it. This is a very high performance, perceptually lossless synthesizer, and it is a very intuitive and white box model of creating a speech codec. Now, let's go back to what we started the talk with, is like, how do we link this to the brain? We've talked about the alignment between AI and vocal tract. Let's talk about the brain now, right? In brain, we typically talk about both the neural encoding and neural decoding. So neural encoding is where you want to make sense of what's happening in the brain, given what is happening in terms of the stimulus that was presented or the behavior that was expressed, right? And in decoding, you're using what the brain is doing and converting it into something that should happen in the world. And kind of the very first work that really showed the power of both the ECOG technology, electrocardiography, and also like speech neuroscience really is this paper from Eddie Chang's lab at UCSF, which also kind of piqued my interest in this area and made me join his lab as a postdoc then. But what this work did was create a map of the vocal tract in the brain by simply having people say simple syllables like ba, da, ga, and then seeing what's happening in different articulators, in different electrode locations, right? And what I was interested in and what I started in my postdoctoral work was, well, how does this, we simply do not speak in discrete chunks of syllables. We actually speak fluently, and there is all this blending that happens for the articulation to emerge in a very co-articulated fashion, right? So I started this new task for recording people speaking complete sentences. So here, artificial intelligence is for real is a sentence someone would say, and we would record what's happening in the brain. We also record what's happening in the acoustic form, and then I talked about how we can go from acoustics to articulation. So that's what we do. So what we then did was this encoding study. So where we have behavior that is characterized by the movement patterns across various articulators, and then we fit a linear again a regression to go from the displacements into actually what's measured in the brain. So this is the voltage traces that you have on in colored is what's recorded, and in the dashed line is the fit of the regression. So you can see it's very high fidelity regression, and you can project the weights back into what this uh, electrode, this location here is actually caring about. So in fact, what this electrode is doing, if you project it back into the vocal tract, is this action of the tongue tip going and touching the roof of the palate and then coming back, right? So this is when you have like a sa sound or a ta, da, na, all these sounds which involve the tongue tip going and touching and coming back, right? So if I go back again, the phrase that was here, I don't know if you could see it, but it's called stimulating discussions, right? So every time there was a stimulating or a T or a D, the electrode is actually high, right? So that's actually what it's coding. You can see that in the projection as well. That what you saw here was the tongue tip going and touching the back of the upper incisor. In fact, if you just go a little north of that electrode site, if you go here into this red dot, and you do the same regression and ask, what are these weights representing? They actually represent this orchestrated trace of the lips going together and coming back, right? So what's interesting is different articulator positions, different places in the brain are actually coding for orchestrated movement patterns across the vocal tract. Why is this fascinating? The brain is not coding lower lip at once or upper lip at once or just the tongue. It's orchestrated across the board, across the jaw, the tongue, 3 points on the tongue, and the lips together, right? So in fact, that's what we did, and we have this coding of different motifs, spatiotemporal motifs of various parts of the vocal tract. Now, that's what that story was. This was a neuron study in 2018 that kind of seeded the question is like, how can we now extend this towards brain-computer interfaces, right? All of this was the science about what the brain is doing or what the behavior is and how we can explain the behavior. But the question, like the motivation even that got us into this was, how can we go from all of this insights and techniques that we have into creating a technology for communication for people who are otherwise not able to communicate. So if you've seen people with ALS or brainstem injury, it's frustrating what they have to deal with in terms of technology. We now have, like, engineering wise, we have this AI advent and all of this phenomenal technology that exists, but the technology for assistive communication is very, very bad even now. Right, so what you see here is a scale of communication rates of various modalities. Right now, I'll be speaking somewhere between 120 and 140 words per minute, but BCI technology back like 5 years ago was still like sub 10 words per minute. Right, it's really bad. And so the promise of BCIs is, well, in most of these conditions where there is a breakdown of the motor neurons, the pathways are broken, but these folks are cognitively very intact. They are, as smart as they ever were, and they just are not able to, communicate using their existing infrastructure. So in fact, what we did, this was in 2019. We demonstrated that the data that we were getting through ECOG was sufficient to create uh, high intelligible speech. So what we created was not just an AI model again. It's not going from brain data to sound. We actually go from brain, and then we decode the kinematics, the vocal tract movements, because that's what from the encoding study we realized what the coding of the brain is. The neural coding is actually for articulation, which is not surprising because this is the speech motor cortex that we were implanting in, and of course it cares about motor articulation. And then we have kinematics to acoustics that we can synthesize using our vocoding technology, and then that can then be played, right? So in fact, when we first did this, like I tried a bunch of things, none of which worked. But then after we had this biomimetic model, biomimetic because we are not going to speech, we are going from brain to speaking apparatus to sound, which is really how the biology actually happens. So that was very reassuring that we've seen spectrograms. So this is actually what a person actually spoke as they were being recorded in the brain, and this is what we are able to synthesize. So that was good. Silence was silence, so that's good. In fact, so what we've then done is synthesize what we can hear. And so I'll play the sound of what we can generate from the brain.
Shipbuilding is a fascinating process.
So that's coming from the brain, and this is the original.
Shipbuilding is a most fascinating process.
I'll play this again.
Shipbuilding is a fascinating process.
So if you have been primed, you can kind of make sense that, oh yeah, it is doing the right thing, but it's not high intelligible. But again, mind you, this was 2019, and we've done much more. Again, this is a participant with epilepsy. She's not paralyzed herself, but this was a proof of principle. But after this work came out, like there are several clinical trials that started exploring the possibility of possibly using speech BCI to restore communication in paralyzed people. And we started a clinical trial called Bravo, which is short for Brain Restoration of Arm and Voice. So because the arm region and the voice region are very close in the brain, so with one grid we can tackle both. In fact, since 2019, there is a lot of work that have happened. So there is this review article in Nature Reviews Neuroscience from this year, if people are interested. But a lot of work, some of which I've been privileged to have taken part in, all the way from very simple, can we decode words, to can we decode sentences? Does the participant need to overtly speak, or can they attempt movement? All of these are things that we have explored. And so this is the very first work which showed that even in a paralyzed participant, we can decode movement, intent of movement, and decode. So in this participant, he was articulating overtly, and we were able to get like 25% word error rate and a words per minute of like 15, which is better than the sub 10 word per minute we were having before that. So here is a demonstration of a subsequent paper which actually used that very same technology in a speller like application. So this is the setup. So the participant is implanted on this side, and then there is a pedestal on which there is a USB-C, like the thing that's plugging into my computer right now. And then we are decoding that, we are measuring that voltage, and we have our models. And what the participant is doing is using the NATO code words like Alpha, Bravo, Charlie, Delta. Like, so with 26 letters, we created a speller. So he's trying to respond to that question, going for a walk, all by saying, Alpha, Lima, Kilo, and so on. So it was very limited vocabulary, but he could, limited vocabulary in the neural decoding, but he could synthesize a lot of words together, right? But of course, it's not still natural, and we wanted to explore and like improve it to make it more naturalistic. And luckily for us, we had a new participant, Anne, who had a brainstem stroke 20 years ago. and she cannot move her limbs or communicate through voice. So we implanted the motor cortex, as you can see in this grid here. Um, and what we've done with Anne was very interesting. We wanted to explore larger sentences rather than simple spelling setting. So we actually created three modalities together. We created decoding the text, the decoding the voice, and decoding an avatar of her likeness. So I'll tell you what that is in a bit. So the technology is very similar to what you have in current day speech recognition systems in your Alexa or your Siri. We were using the ECOG. We were predicting what phoneme posteriors were, and then we have this language model that kind of gives you a prior on what are the likely word sequences that happens, which kind of improved then 25% word error rate on like full sentences. But we also were not just interested in the text. In fact, all the first part of my talk was about speech and how it's very naturalistic. So what we did here was, again, use the pre-trained AI models as a representation for what speech should sound like. And we created this sequence to sequence modeling problem because this participant was actually not speaking, so we didn't know which part of her trial was aligned to which part of the sound. So it was not even a supervised setting in a frame level. So we were taking an entire window of a trial of her attempting to say something, and out comes discrete speech units, which are from the self-supervised models that I just talked about before. And that then we vocoded into speech. What we also did was we also used her video from her wedding, where it was a grainy video and then audio was kind of shaky, but we kind of took the embedding of her voice, which we then imposed on the synthesizer, so it sounds like her. The third modality was, of course, the facial avatar. Because we are already decoding movement, we can plug in a face to her and then have it animate what she's trying to say, or even express. So this is her expression decoding. So you can see very many gestures here, lips and jaw and the tongue, and the confusion matrix is very diagonal, which means that we can decode very well what her emotion is. Again, we are not decoding really the mental state of emotion. It's really the articulatory substrate of how emotion would be manifested across the face. And likewise with the emotions that you see here. So here is this is a Nature paper from last year, and this is a demo of what it is. So I'll just skip through because I have more things coming. So she has a sentence, it turns green, and then she attempts. So she's trying to say, "I think you're wonderful."
I think you are wonderful.
So this is coming from that sequence to sequence model. You can see that there is a high latency between the sentence turning green and her sound coming out.
Give me a few minutes.
Right. So it is really a task problem because we do not have alignment with when she is attempting at a phrase level, at a frame level. So we have to wait for an entire sentence. So we wait for like 4 seconds just to collect the data, and then we pass the sequence to sequence model. So this, nonetheless, this was very well received by the community, but I was particularly not very happy with the latency that we were dealing with. So what we have now, and this was accepted at Nature Neuroscience only last week, so this is very fresh, not of the press yet. But what we have innovated since was this very naturalistic design for a speech PCI. And what's naturalistic about this? It is a very streaming synthesizer, so we don't have to wait for an entire sentence. It is like synchronized with her intent to move, and the architecture is as follows. So we kind of run a buffer of her trying to speak, and then we use this a technique called RNN transducers, which are used in edge ASR. Like what you want your Google phone to be like as fast as possible. We can use these streaming models. So this is the streaming model that then once it has enough evidence, it chunks these attempt into speech and then joins them together. So this is a very streamable architecture, and it is we can run an entire block basically of data. So what you're seeing here is 6 minutes of her speaking, and then this is the output of what comes out of it. Like we don't even need a task structure anymore, no go queue or anything. So it is very aligned, and you can see the communication rates are very much improved all the way. So the streaming is almost hitting like 80 plus in this case, and we have also in this paper run the same model architecture, the streaming synthesizer, on ECOG electrode arrays, even the Utah arrays from the Brain Gate trial, and also EMG that we're collecting from the from other participants. But it's really about the technique being very scalable. So I'll end with the demo on how that performs. So this is
You look me there and
you can see it's trying to piece together different words, but you can see the latency is much better improved. I'll just skip through the very last one.
you
Okay. After it turns green, she tries to speak.
I know that, but you can now.
All right. So so that is like the large vocabulary synthesis. With limited phrase set, we can do much better.
I am sorry, but I have an appointment now.
I'll let it play one more sentence and I'll wrap
Let me tell you what I did.
All right. Okay. So this is kind of like really pushing what we can do right now on someone who is paralyzed, like locked in. We don't even need overt behavior from her, but we can with minimal latency. This I think is less than a second in terms of latency from like the cue turning green to her listening to her voice. And what was remarkable was the first time she heard the voice, she was very happy with it. She felt she was embodied, that it was her controlling the vocoder, which was never happening when we were decoding text for her, by the way. So this is really, I think, the future of neuroprosthesis. Now, with or without our help, industry is also interested in it. You see Neuralink already, mean age rising, a wireless, low footprint, implantable. So the technology on the engineering and packaging exists today. What we really need are these human aligned models of how we can make sense of what we are recording in the brain and convert into actionable signals that we can create spoken communication out of. And we really are in a new realm of human-centered AI, because the AI is really literally in the human here. So we have to like design new paradigms on how that can be trained, and then mutually the subject and the AI learning together is, I think, the future. Okay, I want to wrap and leave some time for questions if there is time. Sorry, but yeah, I want to thank my funders and all my students who enable all the work that I talked about today. So yeah, thank you very much.
Thank you for very interesting and amazing work. Now the session is open for questions. If you raise your hand. Yeah. There are 2 questions. Well, the microphone will be one over here and one over. In the meantime, a natural question would be, how do you think about doing the same kind of work in a non-invasive manner?
Yeah, absolutely. I think non-invasive is the eventual target. Like even the latest study that's coming out, we have done EMG, which is relatively non-invasive, still invasive if you have to stick all these things on your face. So I think non-invasive is the way to go. The sensing technologies are getting better and better. But what's truly needed is with whatever sensing modality we use, I think having a very reliable prior, which comes from these aligned AI models, human aligned AI models, is going to be very important in driving the performance up.
Good. Um,
Yeah.
yeah.
Thank you for your really interesting talk, and I'm very interested in your demo videos. And I have two questions. First one is that if you're training the model, you should need the data set aligned with speech, audio, and the EMA and the brain signals, like ECOG or implanted brain signals. So how do you collect the data? How long was the data? How?
Okay. Yeah, I think I understand. The question is about alignment. That is the main question.
Uh-huh.
That is the central question that drove all these developments. Is like towards the end, like the very latest demos that you've seen, there was no alignment at all. It was just brain data, and we prompting her to say something. We are assuming that she was attempting to speak, and we kind of synthesize using a text-to-speech system a target of her trying to speak it unaligned way. Okay, so we are learning. The machine learning algorithm is learning implicitly an alignment between brain and articulation and speech.
Oh, so in the last video, you don't train the model before, you just train the model online?
Oh no, it was trained before.
Oh.
It was trained before, but the target, like I said, was her trying to say that, which is the streaming part, and the target is using a text-to-speech system that we create what it would have sounded like if she was really speaking. So it was not aligned in collection because there was no data to collect on her audio. It was just the brain we had.
So I'm curious, how did you train the model beforehand? Because you don't have her own data, so you trained the model with somebody else's
So it was
data?
the TTS system creating sound that she would have spoken. And we have the window of her attempt, we have the speech signal. Now we are training that transducer to go from buffers of brain data into speech. Right? So implicitly we are both learning an alignment and a function that transforms brain into speech.
Okay, thank you.
Okay, there was another question.
Yeah.
So thank you for the talk. Actually, I have tons of questions here, but I think because of time limit, I'll only ask two of them. So first of all, because you mentioned about human AI alignment, so basically when I'm also working in human robot alignment problem, but missing the navigation test, but I'm curious, like in the alignment problem, people always ask like whether we should do what human wants or what is correct. So how here I also saw you include what was said a large language model or only language model. I guess it's here for correct the grammar or how to spell the word correctly, but won't it be like something now the human really want, but just something that corrected by the model?
Yeah, I think it's an empirical decision that the developers have to make. Should we do? I think eventually there will be a shared autonomy between the human and the AI. So the autonomy is shared. It's not AI should not be autonomous, neither should the human because they cannot do it. So AI should just fill the missing details. So whether it's the spelling, sure, that should be done, but it shouldn't change. It shouldn't hallucinate the intent. So because that would be like killing the point, basically.
Like a bidirectional alignment.
Yeah, exactly. Human and AI. So I think learning itself might also be bidirectional.
So you think like maybe human here is also trying to adapt to what?
Oh, very definitely. Plasticity is a very big deal. In fact, what drove all the cochlear implant, even though the coding in the cochlear implants is bad, is really learning and plasticity of the brain that you can learn to decipher between even bad signals, right? So even with the bad vocoder, to our misfortune, the participant was explanted long before we could do longitudinal studies. So we could not really report on the plasticity, but that is the goal. We have a new participant coming up next month. So we are hoping to see them actually co-learn with the AI so that they can speak and also learn to speak better.
Very good. There are more questions, but
I'll be available, so please catch me.
Yeah, we're limited in time, but Professor Anumanchipalli will be around, so catch him up after the session.
Thank you very much.
Thank you.